Hello friends, today we will talk about the some part of linear algebra. Uh, these questions are very much basics related to matrix, the diagonalization of the matrix and the projection concept. So these problems related to this previous year's GATE examination. So first I will take one problem. I just want to write the problem, what's going to be. Okay. So the problem is we have a matrix. Uh, just a minute. Okay. Now we have this. Just a second. Getting a few problems here, few technical issues. Okay. Okay. Now things are working. Suppose we have this matrix like 3 cross 3 matrix. It is minus 1 plus uh, I root 3 by 2 and minus 1 minus I root 3 by 2 and like the first row is 0 0 0 and 0, sorry, here we have 1 0 and 1 plus 2i. Yeah. Okay, so this is going to be a matrix and we have to find out, suppose this matrix is A. The question is we have to find out the trace of A power 120. Okay, this is the question. So okay, so this is the problem. Now we have to reach on to this A power 120, which is typical. So we'll have to, take few properties related to matrix. So here we have a matrix. See carefully. This matrix is actually what it's um, yeah. This one element is missing. I think it's zero here as well. So this is actually an upper triangular matrix. So if we talk about the eigenvalues of this matrix, then definitely we know that the diagonal elements are actually the eigenvalues of this upper triangular matrix. So we have three eigenvalues here: 1 minus 1 plus I root 3 by 2 and minus 1 minus I root 3 by 2. So these are the eigenvalues. So using eigenvalues we can reach on to the trace. Okay, so since these are actually the cube root of unity, so we can assume it like 1 omega and omega square. So suppose This omega is nothing but this minus 1 plus uh, I root 3 by 2, and omega square is minus 1 minus I root 3 by 2i by 2. Okay, okay, so what we have to do here, we know that this we have to find out the trace. That is, trace means the sum of diagonal elements. So, and it is also equal to the sum of eigenvalues. We all know that the sum of eigenvalues is equal to the trace of the matrix. So, what is going to be the sum of the eigenvalues? So here we are talking about the sum of eigenvalues of a power 120. So definitely, if we take the trace of a power 120, it will be the sum of uh, yeah. And if we talk about the eigenvalues of a power 120, they will be the eigenvalue, the power 120 of these three eigenvalues 1 omega omega square. So the trace will be the sum of these three. So 1 plus omega power 120 plus omega square power 120. Okay, so now here actually they are talking about this trace of a power 102, not 120. So we can change here as well, 102. Okay, and okay, so we can using simple calculation now we can easily write omega cube. It's gonna be 34. 3043 is 102, and omega 6, and it is again it's going to be 204. So uh, we can write it as, if we divide 204 by 6, we get 30, 204, it's 24, again 38. Right? Okay, so now we know that omega cube is equal to 1. So this is actually 1 plus 1 plus 1. So this will be 3. So the trace of a power 102 will be 3. So this is going to be the answer. So this is a very simple problem related to this matrix, eigenvalues and the trace of a matrix. Now uh, we can take another problem. Okay, now we can take another problem using this 2009 GATE examination previous year's paper. Okay, so this is actually a problem related to this diagonalization of a matrix, which is most important topic for this GATE examination. Okay, so what is the problem? Now we all know that the diagonalization of a matrix is said to be diagonalizable if all the eigenvalues of a matrix are distinct, or we can say that the algebraic multiplicity of a matrix is equal to the geometric multiplicity. So of an eigenvalue, not a matrix. So here we have a problem. We have given four matrices and we have to find out that which is not diagonalizable. These four matrices are actually okay. So these four matrices are 1, 1, 1 2. Second one is 1 0 3 2. Third one is 0 minus 1 1 0. And 1 1 0. So we have to find out that which matrix is not diagonalizable. Okay, so here if we talk about the first matrix, okay, so this if we talk about the eigenvalues of this matrix, um, actually we are trying to find out the eigenvalues first. Okay, if both the eigenvalues are distinct, then we'll say that the matrix is diagonalizable. So here we have we have this sum, the trace of the matrix is 3. Then for in first case the trace of the matrix is 3, and the determinant is actually determinant is nothing but 1. So what are the possibilities? We have two eigenvalues in first case. Sum is 3 and product is 1. So definitely we have uh, two eigenvalues which are distinct. Okay. So we can say uh, what's going to be the case. Trace is 3. Lambda 1 plus lambda 2 is 3. And lambda 1 into lambda 2 is 1. Okay, see, find out lambda 1 from here, 1 by lambda 2. So lambda 1 plus 1 by lambda 1 we can write is equal to 3. So lambda square minus 1 is plus 1 is minus 3 lambda 1 is equal to 0. Okay, so we can find out this lambda 1 actually. It is equal to this minus b plus minus under root b square. It's 9 minus 4ac upon 2a. So this eigenvalue is actually in a complex form. Okay, no, not in complex form, but it's actually an imaginary number, not real. So, and we get the third one, which is negative of this. So these two eigenvalues are distinct. So you'll say that this matrix is first matrix is diagonalizable. In second case, we have upper triangular matrix. So definitely we have eigenvalues 1 and 2, and both are distinct. So it is diagonalizable as well. In third case, we have trace 0 and determinant 1. So on that case, we have two eigenvalues plus 1 minus 1. So in third case, distinct value eigenvalues, so definitely diagonalizable. And in fourth case, if we talk about the fourth case, 1, 1, 0, 1. In this matrix, um, we have eigenvalues, which is actually this matrix is what the lower triangular matrix. So eigenvalues are 1, 1 repetitive, but we'll have to check that either it is diagonalizable or not. So we can apply one property, which is uh, since lambda is equal to 1 repetitive manner, so you'll find out the algebraic multiplicity of this 1 is definitely 2 here. If we find out the geometric multiplicity, we will have to subtract 1 from the diagonal elements, so it will be 0 0 1 and 0. So what about the nullity of this matrix? It is 1. So the GM of this matrix is actually 1. So AM and GM both are distinct. So in that case, this matrix is not diagonalizable. So this is going to be the answer. Okay, so in this problem, we have talked about this diagonalizability of a matrix using the concepts. The If a matrix have different eigenvalues, the matrix is diagonalizable, and if AM is not equal to GM for any eigenvalue, then matrix matrix is not diagonalizable. So this was the second problem. Now we can take a third one. uh, okay, now we can take a third problem. uh, Third problem is related to the projection. Now the third problem is, if V is a column matrix of a given matrix. Okay, okay, so V is actually a column space of the matrix. Then the orthogonal projection of another matrix on V is what? They are saying that this capital V, uh, see, this capital V is actually the column space of the matrix. Column space of matrix A, which is equal to uh, this. Okay, and then they are saying that the orthogonal projection of orthogonal projection of 0 1 0, column matrix 0 1 0 on V is what? Okay, so this is actually a question. Okay, so here they are saying that capital V is a column space of this matrix. So we have two columns in A, so definitely we have V, which is a vector space of two vectors, and two vectors are actually 1 1 2, and another one is -1 2 and -1. Okay, so these two are, suppose these two vectors are w1 and w2. Okay, and they are saying that orthogonal projection of this on V. Suppose uh, this new vector is small v, and then the orthogonal projection will be, we'll talk about the inner product. The inner product of VW1 upon inner product of W1 with W1 into W1 plus inner product of VW2 upon W2 and W2 in inner product into W2. This is going to be the orthogonal projection. So we'll find out the values now. These inner products will be these scalar quantities. So VW1, if we talk about VW1, so we have small v this and W1 this. So just find out the inner product of these two, 0 1 0 1 1 2, and that it's gonna be 0 into 1 is 0 plus 1 into 1 is 1, 0 into 2 is 0. So 1 into 1 is 1. If we find out the summation of these three products, it's gonna be 1, and W1 into W1. So we have 1 into 1, 1 into 1, and 2 into 2. So this overall sum will be 6. Okay, so this is going to be 6. and then W1, which is 1, 1, 2. And the next term is inner product of WW2. So we have 2 here, and again 6 into minus 1, 2, minus 1. So what's going to happen now? It will be first vector is 1, 1, 2, right? Now the first vector is 1, 1, 1 here. So if we talk about W1, VW1 is going to be 1 plus, yeah, it's going to be 1, and then W1, W1 is going to be 1 plus 1 plus 1, so it should be 3 here. This is going to be 2 by 6 again, so it will be 1 by 3. So 1 by 3 is taken as common, and we'll add these two vectors here. So we get 0, 3. We have 1 here, 0. And if find out the product, we'll get what? 0, 1, 0. So 0, 0, 1, 0 will be the projection of this column space. Now projection of this 0, 1, 0 on B. That is, the projection is same. In that case, we'll say that uh, matrix, this vector is actually a part of this matrix. Okay. So in this lecture, I've talked about a few basic topics related to linear algebra, which can occur in your higher mathematics examination. So in the next lectures, we will take more problems and more subjects. In the previous chapters, in the previous lectures, I have talked about few problems related to modern algebra. Now we have taken linear algebra. So many topics are remaining. So in future, we will take few more topics with new problems, new concepts. So thanks a lot for watching and listening. Thank you. And have a very, very, very happy new year to everyone.